Assalamualaikum warahmatullahi wabarakatuh. Good day everyone. I would like to say thank you for click this video. Let me introduce myself. My name is Tito Alvi and I would like to present our research paper with Mr. Jahrizal Sumabrata and Professor Kalamullah Ramli about design and implementation of railway dynamic twist early detection system to improve railway safety. This research is conducted in Department of Civil and Environmental Engineering, Universitas Indonesia. First, we will talk about introduction. According to statistical data from Indonesia Transport Safety Committee or KNKT, that train accident in Indonesia are mostly caused by infrastructure that is equal to 69% of the total of all the main causes of accidents. Based on the KNKT investigation report number 19030102 on 2019, stated that the type of track twist caused accident that occurred had a contributing factor, namely problems with the rail infrastructure in the form of irregularities. Detection of irregularities, especially track twists in Indonesia, is carried out in the process of maintaining railroads using special trains with certain time, so that it takes a long time you have to wait for the track maintenance cycle. So to reduce this accident, we need a preventive system that can be operated seamlessly so that similar accidents do not happen again. Problem identification. According to the KNKT investigation report, there are specific problems that results in train accidents, namely irregularity in the form of dynamic twist. The most cause of accidents are derailment, and the contributing factor is infrastructure problem. Irregularity measuring instrument to detect track twist in Indonesia still use manual tools. And then irregularity track problem is detected after an accident occurred. For this research objective, first, designing a system capable of detecting irregularities of train tracks, especially track twist, and then implementing a detection system that providing early warning to train operator so that to prevent train accident caused by track twist again. And then test the capability and reliability of the system that has been implemented. And the last, comparing the result of testing tools that have been implemented with manual measuring tools that are commonly used. Next, about literature review, we will talk about first track irregularity according to Liu Niu and Jiao Hao Yun Lai Zhou 2020 about track irregularity assessment. Track irregularity is a condition that refers to the deviation of the geometry, size, and location of the road relative to its normal pattern. There are two types of track irregularities, namely static and dynamic. Static irregularity occurs when the railroad track is not loaded with train, while dynamic irregularities occur when the railroad tracks are being burned or occupied by train. As you can see in this figure, it shows about vertical profile. In this research, we will talk about vertical profile. It's called track dynamic in vertical profile. And the next, we will talk or discuss about track twist. Twist is a condition where there is a difference in the actual height between 2 points along the 3 meters or 6 track rails due to a void that occurs under the rail track. As you can see in this figure, there is void under track. This is called track twist. And then derailment accident happened in several countries are caused by the dynamically increasing track irregularities dynamically. due to the wheel load and the lateral force acting on the track when the vehicle running in the section where the track materials are deteriorated. Next, we will talk about track twist characteristic. First, as you can see in this figure, track twist can be calculated by gradients. Gradient is PA or reading 1, this red dot, minus PB or reading 2 in millimeters or blue dot, divided by L. L is distance between the two readings. In this case is 3 meters. For example, if reading 1 result 0 millimeter and then reading 2 15 millimeters, so we can calculate gradient equals change divided by distance. So in this case, gradient equals 15 millimeters divided 3000 millimeters or 3 meters. So gradient is 1 divided 200. So twist reported as 1 in 200. We will talk about existing measurement instruments. This is existing measurement instruments used by operator in Indonesia. And this is the left one, void meters. It has characteristic first, it used manually and then only used during maintenance or rarely. And the right one is measurement train, especially for maintenance. Characteristic one only used during maintenance and then unable to provide early warning system. We will discuss about methodology. In this research, the research was conducted as a part of an effort to provide solution practice. This applied research aims to design an early detection system, the irregularity of the dynamic track twist, so that it can provide early warning, so that the problem of the track can be known earlier. And then this system will be evaluated for success in carrying out the detection, especially for track twist. And primary data obtained from the testing phase can be analyzed to draw an evaluation or whether the system created is in accordance with the plan. Next, we will talk about research process flowchart. First, this research is start from problem identification, from background and research objective. And then the next process is system planning, secondary data analysis, and planning system interface for implementing the system. And the next start to implementation system implementation, implement track twist early detection system based on planning. And then system tests do one first collecting test data and then analysis of test result. And the next, we evaluating, is the system running as planned? If yes, go to conclusion about research conclusion and research advice. If no, go back to system implementation again and then fix the problem with the error if so the system can work as a planned. And next, we will talk about system interfacing. This figure shows two different modules. On the left side is endpoint modules, and the right one is control center modules. The endpoint module that will function to retrieve primary data that describe the status of the track and then transmit data from the rail infrastructure to control center. This module consists of battery, microcontroller, LoRa wireless communication, ultrasonic sensor, and digital clock. This system will receive data from the sensor and then proceed by the controller and send in the form of packets to control center using LoRa wireless communication. And then the second module, red one, is a module that functions as a receiver in the control center. This module will receive data from all endpoints sent by the module on the railroad infrastructure. This module consists of processor and wireless communication module, monitor output, buzzer, and LCD to check the status of the control center module. Next, system installation. Endpoint modules or nodes are placed on the rail sleepers to measure the track twist value. The control center module is placed at the railway operator office to receive notification if a track twist is detected that exceeds the limit or potentially dangerous. By implementing a LoRa wireless network, the entire endpoint module can communicate remotely with the control center module. This is system implementation. The system will be placed on the track sleeper with 3 meters apart between endpoint module. 3 meters according to the track twist definition. As you can see in this top view, 3 meters between the module. The system will measure the vertical change that occur in the track sleeper to determine the depth of voids under the track. As you can see, sensor reading in this red line, it will measure vertical change in this sleeper. Next, we will talk about result and discussion. This is system testing process. Turun deh. Nggak terlalu berubah ya? Nggak terlalu goyang. We will talk about test results. As you can see in this table, the test was carried out for 2 hours by passing by 9 trains, train 1 until train 9, with the type of electric train and diesel locomotive. There are 7 electric train and 2 diesel locomotive. As you can see, in this table, system detection result and void meter measurement as manual or existing measurement instrument now. The test results are compared with manual measuring instrument or void meter and produce the different values or margin of error. The difference in value is expressed in the margin of error with an average value, as you can see, 5% or 95% success rate. The inclusion of this research. First, the system design has been successfully implemented in the form of an endpoint system that can send measurement data to the control center module wirelessly every 0.5 seconds. Train Train operators in Indonesia can monitor track twists on several rail sections using only one control center module because it uses long-distance wireless communication or with LoRa protocol wireless communication. And then the system has been tested and produce an accuracy rate of 95% compared to manual existing measurement instrument. Thank you for listening to my presentation about our research. If you have questions or suggestions, please type it in the comments column or contact this email. Contact me. You can contact every time. And thank you again.